So next we're going to work through some examples of some initial value problems, a very common thing that you'll see in Calc 2 as well as differential equations. So here we have f prime of x is equal to 1 plus 3 square roots of x, and the initial condition given to us is that f of 4 is equal to 25. So first thing I'm going to do is do the same thing that we would do for any square root, which is refer to it as x raised to the 1/2 power. From here, I am ready to anti-differentiate f prime. When you take the antiderivative of a derivative, you wind up with the original function. And we'll go term by term. The antiderivative of 1, well, that would be the function whose derivative is 1. In this case, that would be x. 3 is a constant multiple, so we'll ignore it for the time being. For x to the 1/2 power, we increase the power of x by 1. And then normally we would say then divide by 3/2. But division by 3/2 would be the same as multiplying by the reciprocal of that. So we'll call this 2/3 times x raised to the 3/2 power. Because we're done with our antiderivative, we can now tag on that plus c. Then we'll use algebra to simplify this expression a bit. The 3 will cancel with the 2/3 to leave us with 2x to the 3/2 power plus c. And this is, again, what f of x is equal to. Now with that in mind, we'll now use our initial condition to solve for our plus c. So this is plug in x equals 4, and you'll get that f of x is equal to 25. So 25 is equal to, plug in x equals 4, so 4 plus 2 times 4 raised to the 3/2 power plus c. Now 4 raised to the 3/2 power is a fancy way of saying take the square root of 4 and then cube the result. Square root of 4 is 2, cube the result, we get 8. Then we have an extra factor of 2, and we'll make that 2 separate steps. 2 times 8 gives us 16. And then 16 plus 4 gives us 20. So 25 is equal to 20 plus c. One step of algebra will let us solve for our c. And that'll be c is equal to 5. So we're going to take the function with the generic plus c attached to it and recopy it with the now known value of c. And this will be the solution of our initial value problem. This is f of x is equal to x plus 2x to the 3/2 power plus 5. Now, I realize it seems pretty straightforward when it's just the power rule and, just one antiderivative, so let's bump it up to the next level. Here you'll be given a second derivative, and with that second derivative, because you'll be anti-differentiating twice, we need 2 initial conditions, one for the derivative and one for the original function. So f double prime of x is negative 2 plus 12x minus 12x squared. Let's take an antiderivative according to the power rule. Antiderivative of negative 2, for a constant that would be negative 2 times x plus 12 times. For x, that'll be power rule once again, so increase the power by 1, divide by the new power, or multiply by the reciprocal of that power. Do the same thing for x squared. Power of x goes up by 1, multiply by the reciprocal of the power. Because our antiderivative is now done, we can tag on a plus c. I'm going to do one step of algebra to hopefully simplify this expression a bit. Simplify the 12 over 2, we get 6. Simplify the 12 over 3, and we get 4. And again, this is what f prime of x is equal to. Good news is, we have an antiderivative, an initial condition associated with this. If we plug in x equals 0, then f prime of x is going to be equal to 12. Good news is, that's exactly what we have at this step of the game. So 12 is equal to negative 2 times 0 plus 6 times 0 squared minus 4 times 0 cubed plus c. This is going to be very straightforward to solve because most of the right-hand side drops out. In fact, everything but the c drops out, and we get that c is equal to 12. So recopying down what f prime is equal to, we can now plug in our plus c. So this will be negative 2x plus 6x squared minus 4x cubed plus 12. That is now our first derivative. If I take another antiderivative, I will be back to the original function f of x. So, anti-differentiating all of these terms, x, we apply the power rule. Power goes up by 1, divide by the new power. For x squared, power goes up by 1, divide by the new power. And for x to the third, power goes up by 1, divide by the new power. For the plus 12 that we got, that'll now be plus 12x. Now technically we've already used plus c in here, so I'm not going to reuse plus c. I'm going to pick a different constant, and we'll just call it plus d. I will still be responsible for solving for that d, and I'll be using the initial condition to do so. Before I apply the initial condition, though, I want to rewrite this having simplified some of these expressions. So simplifying using a little bit of algebra, that gets us to negative x squared plus 2x cubed minus x to the fourth plus 12x plus d. Now I get to grab the initial condition from up top. This lets me know that if I plug in, hey BB, x equals 0, the original function will become equal to 4. So that's what I'll do at this step. I plug in f of x is equal to 4. I can plug in x equals 0 everywhere else. Now, just like what happened for the other one, for this guy up here, most of the right-hand side is simply going to drop out, and we'll wind up getting that d is equal to 4. So what I'm going to do is take what I had for f of x and recopy this with the value of d plugged in. That was negative x squared plus 2x cubed minus x to the fourth plus 12x plus 4. And that will be my final answer for f. Now there is one other variety of problem that we should probably talk about, and that is when the initial conditions that are given to you excuse me, are not for the first derivative and the original function, rather they are both for the original function. This strategy is going to be a little bit different because we won't be pausing after the first derivative to plug anything in because we have nothing to plug in. Rather than an initial value problem, this is very frequently referred to as a boundary value problem, when two different initial conditions are given for the original function, not one for the first derivative. So let's start taking those antiderivatives. We'll get f prime of x is equal to, looks like pretty much power rule all the way across here. This will be 4 times x plus 6 times. Power of x goes up by 1, divide by the new power. And for x squared, power of x goes up by 1, divide by the new power. We'll also get a constant of anti-differentiation. We'll call that plus c. Simplifying the expression ever so slightly, we'll get 4x plus 3x squared plus 8x to the fourth power plus c. At this point, we have no initial condition for the first derivative to plug in. So, we don't. We'll just take another antiderivative. F of x is equal to power rule for the first three. Excuse me, that should be a 3, not a 4. My mistake. Guess I was looking ahead because it's about to become a 4. Power of x goes up by 1, divide by the new power. Power of x goes up by 1, divide by the new power. Power of x goes up by 1, divide by the new power. And then we get to our plus c. Well, c is referring to a constant, and when you anti-differentiate a constant, what you're going to wind up with is the constant times x. That's the way that it worked for 4. That's the way it's going to work for plus c. However, because you've just completed another antiderivative, we are going to need a second constant in here. So just like we did for the last example, the second constant, I'm going to give it a different name. Now at this point, we can simplify all of the other expressions that we have here to get the following function. So 2x squared plus x cubed plus 2x to the fourth plus cx plus d. Now that we're done, we can now start plugging in our initial conditions, and I'm going to start with this one. F of 0 is equal to 3. The order in which you apply them is completely arbitrary, but if I have the option of plugging in 0 or plugging in 1, plugging in 0 sounds more fun. So plug in x equals 0, we'll get that f of x is equal to 3. So that'll be 3 is equal to 2 times 0 squared plus 0 cubed plus 2 times 0 to the fourth plus c times 0 plus d. Same thing as what happened on our previous problem. Most of the right-hand side is going to wind up canceling out. We're just going to get that d is equal to 3. And it's okay that we solve for d first. No harm, no foul. So I'm going to recopy our original function. F of x is equal to 2x squared plus x cubed plus 2x to the fourth. We still don't know c, so we'll copy it down as cx, but we did solve for d. We know that d is equal to 3. Still have one more thing to solve for. We still have one more initial condition, so let's do that. This says that if I plug in x equals 1, I'm going to get that f of x is equal to 10. So let's go ahead and do those things. Plug in f of x is equal to 10. We'll get 2 times 1 squared plus 1 cubed plus 2 times 1 to the fourth power plus c times 1 plus 3. Simplifying this expression, 2 times 1 squared is 2, 1 cubed is 1, 2 times 1 to the fourth is 2, c times 1 is c, and plus 3 is plus 3. So that lets me know that 10 is equal to, combining 2 plus 1 plus 2 plus 3, that'll be c plus 8. Solving for c winds up giving us c is equal to 2. So final answer for this function is going to be f of x is equal to, recopy the function one more time, 2x squared plus x cubed plus 2x to the fourth plus cx is now 2x and plus d is now plus 3. That will be our final answer for this function. Wow, good stuff.